Good morning, students. Today I'm going to teach the course Basic Electronics. In that course, we are going to start with Module 1, where you are going to learn about semiconductor diodes and applications. The topics which I am going to cover here are Introduction to Diode, PN junction diode, zero biased PN junction diode, reverse bias PN junction diode, forward bias PN junction diode symbol and static VI characteristics, and finally the ideal diode and practical diode symbol and equivalent representation. So let us know what is a diode. A diode is a two-layer device which facilitates conduction in one direction and stops conduction in the other direction. And it has got various range of applications such as rectification, converting AC to DC, voltage regulation, protection against high voltage, and wave shaping. Also, we have various special purpose diodes available in the market are example Zener diode, light emitting diode, LED, photodiode, photocoupler, and several others. What is a PN junction diode? So I am going to frame a PN junction by diffusing a p-type semiconductor to a n-type semiconductor. Thereby I am going to create a barrier voltage across the diode junction. This you can understand from the next slide. So here I have taken a n-type semiconductor which is diffused with a p-type semiconductor. Thereby can see there is a junction formed which is named as a PN junction. N-type material, basically the majority charge carriers are electrons which are negatively charged carriers, and whereas for a p-type region it is the majority charge carriers are holes and the minority charge carriers are electrons. So these two semiconductors are diffused to form a PN junction diode. So here I am going to analyze this PN junction diode when there is no external voltage applied across the PN junction. So that is why it is named as zero biased PN junction diode. So when it is zero biased, the majority charge carriers electrons from the N region will try to recombine with the holes from the P region. So near the junction you can observe there will be recombination of electrons and holes will happen. So once this recombination is completed, you can see there will be some electrons left near the PN junction of the P region and holes will be left across the PN junction near to the P region. So this electrons and holes will produce a barrier potential which will form a depletion region across the PN junction. So this potential will call it as a built-in potential which is shown down. So this barrier potential or built-in potential, it varies from zero point 0.3 to 0.7 volt based on what type of semiconductor I am going to choose to make a PN junction diode. And you can observe there will not be any flow of current across the junction because there is some built-in potential happened near the junction. And if you see the equivalent circuit of a zero biased PN junction diode, it is shown on the right hand side by a PN junction symbol along with a resistance under zero bias condition. So thereby we can conclude that in the zero biased PN junction diode, there will not be any flow of current and the depletion layer will be formed near the PN junction diode. The PN junction diode can be well analyzed if I am going to operate the PN junction diode in two different operating regions, which are the reverse bias and forward bias. Reverse biased PN junction diode and its characteristics. What is reverse bias? Reverse bias is nothing but I am going to connect an external voltage to the PN junction diode. In the sense, for the N region, it will be connected to the positive of the battery, and for the P region, it will be connected to the negative of the battery. So as soon as this reverse bias is given for the PN junction, the majority charge carriers electrons from the N region will be forced or pulled towards the positive of the battery. Thereby, the depletion region becomes wider near the PN junction. And similarly, the positive charge carriers holes from the P region will be attracted towards the negative of the battery. Thereby, again, you can see there is a wider depletion region formed across the PN junction. So as there is a wider depletion region, there will not be any flow of charge carriers across the PN junction. Why? Because the maximum charge carriers will be attracted towards the battery, and if there is any current also, it will be because of the minority charge carriers from the N region and P region, which will be trying to cross the PN junction. So if that is the case, we can observe there will be a little flow of current across the PN junction. We'll name it as a reverse current. So it is shown in the equivalent circuit diagram next to that. So there is a PN diode which is given a external bias, reverse bias we have applied, and as we discussed, there will not be any flow of current. So the current is 0. It is mentioned as I is equal to 0, and the direction of current will be from the N type to the P type. Down it is shown with an equivalent circuit symbol diode. Below that it is considered as an open circuit. Why? Because there will not be any flow of current across this closed circuit. Coming to the characteristics, we can observe the characteristics is drawn between the reverse bias voltage what we have given for the PN junction diode with the reverse current flowing across the circuit. As you can see from the graph, whenever a reverse voltage is applied, the flow of current, as we have discussed, it is almost less, which is in the order of less than 10 nanoamps. So this region, we'll call it as a reverse bias region. So above 80 or 90 voltage, we can observe there is a reverse breakdown voltage region, which we'll discuss in the next slide. So we can conclude that during the reverse bias PN junction diode, there will not be any flow of current, and if there is any flow of current also, it will be due to the minority charge carriers from N region to P region, and it is very less. Forward biased PN junction diode and its characteristics. So what is forward bias? Forward bias is nothing but we are going to apply external voltage with the help of a battery to the PN junction diode. So N-type material is connected to the negative of the battery and P-type material is connected to the positive of the battery. So as soon as this forward bias is applied, you can observe the electrons from the N region will be trying to cross the junction and it will be forced towards the positive of the battery. In the same way, the holes from the P region will be attracted towards the electrons as well as the forward bias, the negative point. So the majority charge carriers will try to cross the junction, thereby it will produce a drift current which is named as a forward current. So in the equivalent circuit also you can observe there is flow of current and an external voltage is applied which is a forward bias, and the current you can name it as I max. Why? Because the maximum current flows which is taken as the drift current ID. Hence it is written as ID is equal to I max. And below we have shown a equivalent circuit, whereas it behaves as a closed circuit. So it is represented as a closed loop. Coming to the characteristics is drawn between the forward voltage, that is the forward bias applied for the PN junction diode, and the forward current. So here we have analyzed the characteristics for a silicon diode. So for the silicon diode, as soon as the forward voltage is above 0.7, there is a steep increase in the forward current, which is shown in the figure, and it is named as forward bias region. So we can conclude that during the forward bias, there is a flow of current which is the maximum current above the 0.7 volt for the silicon diode. Junction diode symbol and the characteristics, VI characteristics. So here we have shown the conventional flow of current from P to N, and it will be represented in the direction opposite to the direction of flow of electrons. And below we have the complete characteristics. Here we have combined both the forward and the reverse characteristics of a PN junction diode under forward bias and reverse bias. Like already we have discussed, there is a forward voltage for the silicon, it is 0.7 volt. Above that we can expect a steep rise in the forward current, and for the germanium it is 0.3 volt. And the reverse current, you can observe, it is very less. So finally it is the junction diode ideal and practical symbol and characteristics. So as you know, for an ideal diode, the current is completely zero for the during the reverse bias, and during the forward bias there is a steep increase in the current. And for the practical diode, for example the silicon diode what we are discussing now, so the reverse bias, during the reverse bias the current is zero, and during the forward bias, when the forward voltage exceeds 0.7 volt, there is a steep increase in the forward current. So next to that, it is represented the symbol of a ideal diode and a real practical diode which is similar, and the equivalent circuit is, it behaves as a closed circuit, and for the practical diode it is a closed circuit along with a voltage built-in potential of 0.7 volt will exist. During the reverse bias, the diode behaves as a open circuit, and for the practical diode, it can be represented by a open circuit along with a built-in potential of 0.7 volt. Since we are considering the silicon diode, the built-in potential is 0.7 volt. So for the preparation of this video, I have taken the references from the text 1, Basic Electronics by D.P. Kothari and I.J. Nagrath. And then next textbook what I referred is the Basic Electronics by A.P. Godse and U.K. Bakshi. So later we'll continue in the next slide. Thank you.